Hi everyone, I'm Eli and this is Jocelyn, and today we're going to present you Katograph. Others? Okay, so we do a lot of reverse engineering with Jocelyn, and we thought that it might be fun to actually apply reverse engineering technique to games, and that's Katograph. So you see on the slide you have a hashtag, it's Katograph. We put for you a video of the demo of the tool, and also already put a slide, so if you want to gather them, you have the link directly on Twitter. So what is Katograph? Katograph is basically a memory analyzer, which we're going to do patching on-fly games, and we're going to show you how we can do that and how efficient it is to hack modern game. So why are we trying to do that? For multiple things. So you can do a lot of stuff with Katograph. You can first try to have units which level faster. We can also have a way to have infinite monies or any resources you want. And we also have a way to have X-ray vision, meaning we can have, we know what your opponent is doing. And finally, we also have invisible unit. Before we start, let me show you what the end result is. So this is a video of Supreme Commander 2. And if you notice our tank on the bottom, it never dies. See the health bar is keep replenishing. That's Katograph in action. It's basically replenishing the health pool. So do you want to know how we do that? Yes. Okay, so the way we do that is we are doing in-flight memory patching. So view your game as a huge chunk of memory, and what we try to do is to modify it. And if you modify it in the right way, then you end up having a nice effect. So having a building, having an infinite amount of money, and that kind of stuff. So the nice thing about doing in-flight patching of the memory is that it's a generic way to attack game. You can do this on any kind of game you want. It's pretty fast. It turned out that actually looking at the memory and try to reverse a game from the memory is, for me, actually faster than doing a binary analysis. And finally, it's almost invisible because you're only rewriting a part of the memory. So it's very hard for a game to know that to detect that you did cheat. So actually, we have some drawback for this kind of game, for this kind of attack. First, it's really finding a needle in a haystack. For instance, Supreme Commander, we should just show it to you, have about 800 megabytes of data. And what we are looking for, let's say the map is only 1 megabyte. So you're really trying to find a needle in a haystack. The other problem we have, and we're going to show you that, is that when you try to rewrite the memory, we have no direct control over the algorithm of the game. So sometimes we have to find a way to trigger the algorithm to do something for us. And sometimes it works, sometimes it does not. So in some cases, it's not as reliable as patching the binary. So here is what we're going to present to you. First, we're going to give you a quick background of the game. Who is playing game here? Raise your hand. Almost everyone. Okay, so that will be pretty quick. And then we're going to show you how we can actually really build a map hack, reverse a game and build a map hack out of it with Katograph. Then we're going to show you how we are able to make invisible unit on another game. And finally, we'll discuss how we can actually resync the network to prevent being caught when we are cheating online. And finally, if the god of the demo are with us, Jocelyn is going to show you how Katograph code is, and he's going to do in real time a map hack for you, if it works. So, bit of background. We all know that games actually earn a lot of money, about 273 million this last year, and there is a ton of different kind of game. Action game, Mario, first-person shooter, sports game, role-playing game, World of Warcraft. Any World of Warcraft player here? No one is playing World of Warcraft? Few of you? I do. Okay. And some adventure game, not that interesting to cheat on actually. And finally, strategy game. And the one we actually did focus on for this talk is these real strategy games, because they are the ones who are the most sold on PC. We could have done any other type of game. It's just that this one is the most used, so that's the one we go for. For those who never see RTS, and I think there is almost anyone here who never saw it, there is a bunch of, the idea is you want to beat up your opponent, and to do that, you gather resources, and then you accumulate them until you can buy stuff like building, units, and you have what we call a minimap on the corner, usually, which displays the entire map. And you see there is a part which is visible, which is a part you actually show your opponent. If your opponent is in this visible section, you see it. And if you don't, if it's not in this section, it's what we call the fog of war. It's where you don't have any line of sight. And if your opponent is here, you don't see it. All the entire idea of the map pack is actually to remove it. We're going to show you the demo on the most recent game we were able to find. This is Supreme Commander 2. It's a fairly straightforward real-time strategy game. It has been released in March, so it's the most recent one we came up with. The newest one is, of course, Katograph 2. We're going to discuss this in a bit, but we hadn't had the game when we were doing this kind of demo. So fairly recent game, and you see all our unit, and if we move a unit onto the top, you will see that we are able to see the fog of war in effect, and our opponent is going to show up. And all the tutorial for this first part will be to actually lift off this restriction. So, as we said, there is multiple ways to cheat on our RTS. The first one is to try to have more resources. The second one is having more units, some units which are cheaper or have more health point, invincible unit if you want. And finally, you can also do this kind of map hack. So a map hack visually is just this, right? We try to rewrite the memory and fool the game into thinking that we can see everything. So if we are successful, you basically see the entire map. So there is no spoon. It might seem that there is three kinds of hack: one for resources, one for unit, and one for map hack. Actually, it's not true. For our perspective, it's only a bunch of bits, and all we have to do is find the algorithm to figure out which bit is what, and try to flip them in the right order so we can trigger an effect. So it's basically going through the matrix and see it and try to modify it. So how we build a map hack? We had to find a way. The hard part was to find a way to instrument the game in a way that gives us enough information so we know where to look for. So we do that in four steps. The first step would be to reduce the part of memory we want to consider as the potential place where the structure is. Then we want to find it visually, and then we try to understand it by doing some testing. And finally, we just rewrite it on fly, and either one time or multiple times, depending on which kind of rewriting we need. So how we do that is first we acquire the memory. Katograph basically reads the entire memory. That's why we had to move to 64-bit. That's where actually 64-bit is great for us. Is when a game for Supreme Commander 2 takes like 800 megabytes of memory, we have to have at least 6 or 7 gigabytes of RAM to actually hold it in multiple places and do a lot of computation on it. So we work on Windows 7 64-bits. You can't do that in a 32-bit architecture, actually. But memory is cheap, right? So the first step to instrument the game is we first by playing the game, and we try everything except discovering the map, and we're going only to keep what is the part which did not move because we didn't discover the map, so it must be a memory which didn't change. And it should help us to reduce what we are considering. Then in the second step, we're going to discover the map, and only discover the map, and this time we ask only the memory, we only keep the memory which did change. So it helps us to reduce further how many memory we need to consider. And finally, we do a third step just to clean up a little bit more, and we play the game again. And after that, we should have a fairly small chunk of memory, usually 2 or 3 megabytes, where we know the map is in it, and then we have to look at it visually. That's what we're going to show you. So how do we acquire the game memory for real? This is a video of Katograph in action. So we're going to select the process of Supreme Commander, and then we're going to read the memory from it. It takes a bit of time because the memory, as I said, is 800 megabytes, and for each of them we have to store the address and the value. So basically we have to store 1.6 gigabytes of data for this step. So it takes a little bit of time. You click on I'm going to do a map hack. There is a ton of buttons in the interface. For those who wonder, Katograph has been developed in C#.net. So we do that, and hopefully when this step is done, we can move on and try to do something else, which is we try to remove unrelated memory. Same idea. We go back to the game, and then we try to trigger as many stuff as we can, either by creating new units looking at our building, rotating the camera, doing zooming, because this game have a huge level of zoom. So basically we try to change as many memory which is unrelated to the game to narrow down what we have. And then we ask Katograph to remove everything which did change, and this is actually faster, and we're going to basically knock off about 100 megabytes of data which is not related to the map. And it's pretty quick. Then, so you see the progress bar in green in the middle of the video. Okay, so when this is done, we have to do the most important step. We have to use a couple of units to discover the map, and then keep only which part of the memory has been changed. Actually, we never have a clean screenshot because a lot of things are happening all the time. But it's really reduced the map from about 600 megabytes to 2.5 megabytes. So let's see that. So you're going to see on the video, I'm going to move 2 units to the bottom left of the map. You will see them right now. Here they go. So 1 and 2. So basically I'm discovering the bottom left of the map and try to remember the shape, because that's the one we're going to look in the memory. So when we have that, we do a third step. Which is, as I said, similarly to step 1, we're going to redo a change we're going to remove everything which will change by just playing the game a little bit more. Okay, I think I skipped the video. Okay. So same thing, we try to move a little bit. It doesn't have to be long, it's just really efficient. At that time, we probably will remove half of the size, going from 2.5 to 1.2 megabyte of data. And when we're done with that, we need to find the memory, the map in memory. So now we have reduced as much as we can. We now really have to look at the memory and try to figure out where the map is. So we have one working assumption. It turns out to be true in almost every game we look at, is that the map is stored into a 2D array. Actually, you can have multiple maps into the memory. Jocelyn is going to show you this live in the demo. But for now, we just assume that the map is one array in 2D, and if you look this using visualization techniques, what you're going to observe in memory is something like this. So you should be able to see with different colors a 2D array which pop up in the memory we have acquired. So let's do it for real. So first we're going to select the snapshot we want. So we have only one snapshot now, which is the one which is the memory we did remove all the part, and we're going to use what we call a heat map visualization. The heat map visualization is simply having 1 pixel for each bit of the memory, and assign different colors depending on the value. And if we scroll down to it, I'm not sure it's very visible on the screen. On the bottom of the map, you have a very strange shape. Can everyone see it? You see on the bottom of the shape? You see the shape on the bottom? It's like a tilted line, right? It exactly looks almost like what we have as the 2 unit. Yeah? Okay, so I'm going to show you a zoom of it, but that's the idea. So that's exactly what we see from Katograph. And we're going to try to isolate this potential map. If you look in memory, here's what it looks like. This is, on the left, this is a game. On the right, this is what we can have by doing a heat map visualization of this part of the memory. So you see it really looks like the map we have in-game. And Supreme Commander 2 is a specific kind of map. It's what we call an additive visibility map, meaning that every time you have a unit, it actually increases the value with 1 by 1. So if you have 2 units, the value will be 2. If you have 3 units, the value will be 3. So basically, every time you move a unit, it actually subtracts or adds visibility point to all the map. So the way we're going to hack it is we're going to rewrite the entire memory with FFF, meaning that we have 255 units which are actually able to view each square of the map. And we're going to do this continuously into memory, because every time you move a unit, you actually decrease it. So at some point, if we don't do it, the map app tend to fade. So how we came up with the idea this is an additive structure is because we were able to use another trick, which is called a diff map. So remember, this was the situation of the game, and what we're going to do is we're going to move 1 unit, right? We know where the map is, so what we're going to do is we're just going to move the unit from bottom to up and have 2 different positions, and we're going to use what we call a diff map. So the diff map is basically a heat map with 2 colors. Blue means nothing changed, red means change. And if you look here, we're going to put you side by side with the previous map. You see that the only spot which did move was the one where the unit was, right? Everyone sees that? Okay, so far so good. So now we can look at the value. You see the tooltip of Katograph actually display you what the value is. So we know what the value was before and what the value is now. So we can have a guess of how the algorithm works. Once again, we're only comparing with the storage structure, not the algorithm. So we have to count on the game to actually reprocess the storage structure, and sometimes it works, sometimes it does not. So at that point, it's almost done, right? We know what to rewrite, we know where to write it, so it's basically just spawning a thread and writing the memory of the game. And do you want to see how it looked like? Okay, good. So here is the video when you try to rewrite it. So it's an in-game visualization of it. So as you see, on the top, there is my opponent. I can't see it. That's the fog of war. And we just rewrite it right now as we speak. So what will happen is it will pop. And you will see that the game will really believe that, see, here you go. And as you see, the game is completely full, believing that we can see everything. And our defense tower are starting to shoot at the unit. We can even click on the building. It's completely invisible. At that point, you have a full map hack. Pretty cool, right? Sure. So, how many of you did order StarCraft 2? Oh, StarCraft 2? Yes, just released, right? And some of you, as the most. So we wanted to show you how to do that for StarCraft 2. We didn't have time, sorry, but we have something for you. So this is StarCraft 2, and we are not ready to. We tried to do it, but it was really quick. Game been released 2 days ago. So what we have is we were able to find the minimap. Doesn't mean that we can rewrite it to actually make something useful of it, but we are able to find it in memory. If you see, it's just in mirror side, but you can see the minimap. So we are able to actually already find the minimap from StarCraft 2. So it's really, this approach can work on any modern game we know. If you have any other idea of game you think we should try, you can just send us a tweet or email. We'll be happy to try. By the way, we're not going to release the tool. Sorry. And sometime, we were at the lab really late at night and we tried a bunch of games and we have some unexpected effect. So we want just to show you one to see what odd thing we can come up with. So I think it was like two months ago. Yeah, 2 months ago we tried to do Anno, which is a strategy game, and we were messing up with the visibility map. So we were trying one effect here, and we had Frap running, and we just tried to put our boat into the fog. Well, in a way we did succeed to find the map. We just make it a fog permanent. Yeah. The underlying reason why it's not working is because actually when you remove the fog, the algorithm do not reprocess the map, so you can't actually remove it because it's already removed. Just you don't know it. That's the kind of effect. We have a bunch of video like this. In Civilization 4, for instance, we were able to have the map completely disappear. Don't see anything else. That kind of side effect, right? So when you tamper with memory, you never know what happened. A little bit about unit hacking. Unit hack is way, way more harder because this time what we're looking for is probably a few kilobytes of data. And so visualization won't work. You can't actually look at the map and say, here it is, and click on it. So we solely rely on shape analysis, which our algorithm we try to put. Jocelyn made a lot of effort on that. I think he spent night and days for about a month and a half on this. It's really hard to come up with an algorithm which helps you to find the structure with change and understand which structure. So we have one algorithm for each type of structure: stacks, chained list, pointer list, and so forth. To give you an idea how we do that, we have a bunch of heuristics. So if you want to decide to find a stack of pointer, what we do is we make sure that the memory we're considering is only having one integer added every time we create a unit. And we also make sure that this integer is a real pointer. So what we have under the hood is a dereferencing algorithm, which look at the pointer and try to see where it points into the memory. Once again, it's easier said than done, and that's how we do that. The basic idea to narrow down the memory we are considering is simply the same idea. We build unit. We build unit, and every time we build a unit, the possible place where the unit list is keeps decreasing until we have a very short one. small one, sorry. So when we have this memory, we go back to our idea of using visualization, and here you go. This is a visualization of the unit list of Age of Empire 3, I guess, on this one. As you see, we have only like a strip. Each strip represents one unit, so if you have 5 units, it's 5 strips, and the black void between each unit is basically a bunch of memory which is not related to the unit list. So it's really hard then, when we have that, we have to figure out how the units work. Any idea how we do that? Yeah, you get the right idea, exactly. So the way we do that is exactly like this. We go back to the idea of using a diff map. So we start with the unit which is completely blue. The memory of the unit will be blue because we don't move it, we don't do anything with it. And then to know where the coordinates of the unit are stored, we just make it move. And by make it move, we're able to know which part of the memory changed, so we know where the coordinates are. And then we have to figure out how the coordinate system works. And when we know that, we're able to have units which teleport across the map. Pretty cool hack. And the one we really like is we try to have invincible unit, and to do that, that's the way we do is we basically attack our own unit, and we make it bleed, right? So we shoot at them, and hopefully we know by looking where the HP decrease to know where the HP points are. And as a result, you get something like this, right? You get 4 units, which are able to completely whip off a base because they're just not dying. Look, you can notice that our health bar are black. Is because when we rewrite the memory, what happened is we probably also rewrite the color of the bar. We have no way to tell where the color is because it also changed with the health point. But as you can see, we are able to have invincible units, right? Pretty cool. Okay. So now I'm going to tell you the sad part of the story. There is a sad part in the story. Network, right? If you try to cheat on a game on the network side, well, here's what you get. Out of sync. We basically get out of sync because a lot of games actually do some type of checking on the value of the number of units you have, how much health points they have. For instance, if your unit is not dying on your side and is dying on the other side, that something is off. So we have to deal with desynchronization. The way we have to do that is basically you are either able to resync, or you basically get caught. What happened is for some hack, like the map hack, is not detectable by this kind of integrated checking because all you are saying is I am able to see this map, which basically is not triggering that. But if you try to have invisible unit or tampering with the resources, then you get this. So we think we had actually to build on one idea which has been presented at DEFCON 15, and it was pretty cool, which was using the LSP. So the LSP is a layer service provider. It's a functionality provided by WinSock, and it actually allows you to divert some of the traffic to an application if you want. So what we did is we worked with Pascal Ganaye, which is a French guy, which helped us get it run on Windows 7. He started his own project, and we were able to actually intercept packets. And with that, we are able actually to tamper with the traffic, basically by first collecting it and then trying to rewrite it to resync the game. So the way we do that, we do four steps. The first one is we're going to bucket the traffic. When you have a game, you usually have 4 to 7 type of packets. And the way we know there is 5 to 7 type of packets is because these packets have a specific size. And so we're going to only focus on one size at a time because we can compare then what changed and what is not changing. And then we're going to visualize how the change are. And then we try to understand it. Sometimes we are able to do it, sometimes we are not able to do it. And finally, we are able to rewrite the packets. And by rewriting the packet, resync the game. So usually you end up with having not resync. We're not going to tell you how to cheat on a game on the network. Sorry. We're going to show you what the interface looks like, but it's up to you if you want to really apply it on a real game. We know it works. It's just like we don't want to be the one which be blamed because everyone is starting to cheat at Supreme Commander 2 or that kind of famous game. Sorry. But here's the interface. On the left, you have what we call the LSP listener. So the LSP live at the WinSock level, so we have to have a IPC, which is going to speak with the with Katograph, and Katograph will tell him whether to let the packet go or to modify it, and then tell him to rewrite it with a specific value we want. Then we have all the buckets I was picking up before. So for instance, for civilization 4, there is 5 types of packets, and which are sorted by size. And finally, you have the visualization for each bucket. So we can visualize one bucket at a time. A little bit more on the visualization bucket view. So the visualization bucket works like this. On the x-axis, you have the length of the packet. So the rightmost port is the last bit of the packet, and the leftmost port is the first bit. So basically, each block is one different bit of the packet. And on the y-axis is basically each packet are stacked up to the other, so we see the evolution of the trace. And as you can see, and on the top of it, we have something different, which is blue and red, and you should be used to it by now. This is our diff map analysis for the trace. So it tells us which part of the packets are moving and which one is not. Blue meaning not moving, and red meaning it did change at some point. And by just looking and visualizing the trace, you can infer a lot of information on how the protocol works. If it's a fixed value, then you see it's the same color all over the place, right? Like the pink one on the screen. If it's a counter, then that's where the heat map is really useful, is you're going to see a gradient. Do you see it on the screen? So basically you see this is an increment. Every time it increments, it changes color by 1. So you see a continuous gradient. Which means that it's probably a counter. So we don't really have to take care of this until we want to inject something more in it. And finally, you have this part on the right, which is completely look like scramble. It's usually either an IV or an encrypted value with a given key. Although the game we look at didn't have key exchange. So it's a little bit more subtle. It's just more like a specific value for each packet, simply as an IV. Before, Joe is going to try to do a demo real time for you. Just a little bit more of what we're doing now. We didn't did that for only hacking game. What we really hope to do is building more crypto stuff to actually make the game more secure. We should have a lib ready about in 3 months or 4 months, which actually will help developers to build more secure games, so this kind of attack won't work anymore. And we're also working on trying to detect bots, because I kind of hate when I have a bot in front of me on World of Warcraft which gathers everything, and I end up with nothing. So let's pray all together the God of Demo. And who wants to see Katograph real time? So Joe, everyone is counting on you. Pressure.
Okay. So let's hope this works. My micro. This work. Do you hear me? Okay, better now? No screen? Okay, but I have no screen on my side. You see something? Okay. Sorry, technical problem. This one? No. This one? Yeah? Yeah. Ah! Oh, I got your... I see nothing. Ah! Will it be working?
C'est bon.
Okay. Yeah, it works. Okay. It's okay like this. Okay. So sorry, some technical difficulties. So I'm going to show you how to make a map hack on Age of Empires 3 because I'm only using my little MacBook, so I don't have a lot of memory, but it still works and it's still cool. So just starting a game. Here is Katograph. So first step, I will just choose a good process. If I find it, okay. So as you can see in this game, there is 235 megabytes of data. So okay, the game is starting. So first step, I will use the map hack button, and I will just scan all of the memory. So I'm acquiring it. Okay. Now it's done. I will just, like Ellie said you, I'm just letting the game play a little, and so I'm letting my units gather some resources to make the memory change. So now it's done. I'm going to the step 2. If it won't work. Okay. Okay, so as you can see at the beginning I was 235 megabytes, now I only have 196 megabytes. And the third step is the one that reduces the most the memory. So to do that, I will just take one of my units and make it discover the map. So like this I will be able to change the map, the structure of the map, and hopefully I will be able to identify it. Let's move a little. Okay. Okay. So now, like always, clicking. Okay, and now as you can see, I only have 3 megabytes left. So it really reduced all of the memory, all of the data I need. So now I just have to let the game play a little more to reduce a little more of the memory left. Okay, should be enough. Now it's pretty quick. And here is now the interface for the screenshot manager. And as you can see, the screenshot is only 1.8 megabytes. I will use the heatmap to visualize it and hopefully find the map. So here's the heatmap. So as you can see, there is a lot of data left, but not so much. All of the black spots here compress memory space that is not relevant. So there's a lot of stuff. And here, as you can see, we can see like 2 maps, the blue one and the brown one. But in fact, because I know this game already, I know that these two one are only the mini-map. They're not the one I'm interested in. The one I'm interested in should be I think it's this one. Like all this color, here it's not really look like a map, but when I will zoom on it, it will really look like a map. I hope. So here I'm just trying to grab the good memory, the good addresses memory. Here it's done. As you can see here, I have the memory, the true address memory. I just grab, and oh, doesn't work in the middle. Okay, it's a technical problem. I can see all my screen. How can I do that? Sorry. Oh. Why there's some... Why can't I... Je peux pas le voir, je peux pas écrire. How can I do that? I can do my snapshot. I can access my my screen. I will try to change the resolution just for a minute. Hope it will work. Okay, just a second, sorry. Okay, it's better on my screen. I just have to do the manipulation again. Okay, ça devrait marcher. Some technical difficulties, sorry. We'll be back in a few seconds. Oh, you can see it back. Oh, perfect. So, I'm just doing it again. Okay, and someone right here. So as you can see, this is the part that I wasn't able to see. And this is the most important part because it's where I write the memory. So here are the two addresses I just select. I do a new snapshot. Here it is. And I will use a button that try to increase the size of the snapshot just to all the memory, or all the map. And I will zoom a little on it. Something like that. It looks like gibberish, but if I find a way to align it, just have to find the good alignment. I'm not sure. This part is one of the hardest because I have to make it align, and we didn't find a way to make it automatically. Yeah, it looks like I go a little faster. As you can see some shape that trying to appear. I hope. Yep. And here it is. This map is kind of different of the one that Ellie showed you. It's not an additive visibility map. It's a bit mask map. So here's my base. As you can see, the value are 0202, and this is my value. The first the two bytes of high value are my actual visibility, and the two lower, the 02, are what I already saw, but I can't see anymore. Like for example, here I can see, and where's my unit? To be somewhere here. Here I was here, but I'm not here anymore, so I can just show the I can show the game, but not the units. So all I have to do, and everything else, sorry, is the NPC player that have a visibility to and is stored in the same map. So their value are 0, 1. And here must be my opponent, and his value is 0, 4. So everything I have to do is to use a bit mask and do with this value. So, and put it everywhere on the map. So let's try that. So click on bitmap and travel view, very important. And I will do this mask. I will use a thread that to be able to rewrite it all the time, to be able to see the map all the time. And space, sorry. And I launch the writing, and hopefully it will work. I will be able to see the game and all the map. So you can see on the minimap, nothing changed. On the map, it doesn't really look like it were. Sorry, I made the same mistake. So here I just write the memory I saw. I select. So I just have to select the entire map. So to do that, just click here, give me all the addresses of the map, here and here, change, and do the same. Rewrite it. And here, as you can see on the minimap, the unit begin to pop, to appear, and everything began to appear. But it's not working very well because, as I told you, we can't control the algorithm that makes the game appear the map, but we can force it by, for example, changing the resolution of the game that will force the game to rewrite all of the map. So I just have to change the resolution. And here it is. I can see all the map. And that's it. Now you can cheat on your game if you want. It's bad. Don't do that. So, and to conclude, here's the addresses where you can find all of our tutorial and screenshots and keynotes. So to conclude.
So yeah, just to let you know, if you didn't follow everything we did into the demo, we spent a lot of time with Joe to build a tutorial for you, which is about 10 minutes, which actually sums up everything we did. So you can have it on video, and we also put the slide online if you want them. Don't hesitate to share them with your friend. We'll be happy. And if you have any question, it's room 106, and we'll be happy to answer your question. I even show you a little bit more the tool if you want to play with it. Be happy to show you how it do everything. And thanks for attending our talk. I hope you had fun with us. And that's it.